Hey there, sports fans. Way to have you guys back. I'm glad you stuck with us this far. We're entering into our last unit for this school year, solids and elastic moduli. So let's get started into it. Solids and elastic moduli. All solids are elastic due to some degree due to the spring-like structure of the intermolecular bonds holding them together. So what they're saying is imagine there's these springs that are between the molecular and these springs are the bonds between these molecules, and that allows them to stretch or bend or to be pushed in in a slightly different form. But again, we're imagining that's how they're held together. Stress is defined as the force per unit area. So stress is force over area. So let's take a look at an example here. Let's say that we have this rod, and I say it's a rod because it's circular here on the end. I guess there can be square rods as well. But this circular end has an area, and there's a force that's pulling it in both directions. So it's lengthening this. We call this a tensile stress. All right, this is tensile stress. The way we would calculate that stress is we would take this force and divide it by the area of that. Now it could be a square rod, could be a rectangular rod, but we would still take that area of whatever that was and divide it by or take the force and divide it by that area. A compressional stress would be one that pushes in on both ends. So then we would have, we could still calculate that stress as the force divided by the area of the rod. Now we can find out the other forces or other stresses. You could calculate the stress of a knife that it applies. If you could calculate or find the amount of force that was being pushed down and then take the amount of area of the tip of that knife, you could calculate the stress. Let's do a different type of stress problem. Okay, we have a 1,500 kilogram car sits on 4 tires. One tire has a contact area of 6 centimeters by 10 centimeters. Find the stress applied on the ground of one tire. So let me get you started here. So I've went ahead and punched in the equations we're going to use here. The force in this case is the weight. So to calculate that weight, we're going to take mass times gravity, and the mass is 1,500, and we're going to take that times 9.8. And then that means that the force in this case is equal to 3,000, it's actually equal to, sorry, 14700 newtons. Now, if we divide that by 4, we find out then that the force on the weight on one tire is 3,675 newtons. So let's go over here to area. Now I want to find the area. So the area is equal to the length. Well, the length is 6 centimeters, which is 0.06 meters. And then we're going to take that times the width, which is 10 centimeters, which is 0.1 meters. So if we wanted to find that area is equal to 0.006 meters squared. So when it comes to find the area, we're going to take the force, or the weight in this case, of 3675, and we're going to divide it by 0.006, and that gives us an answer of 612,500. And then I don't know if it's going to, if it'll let me put it on here or not. We're going to try, see how this works. We got to stretch this out here a little bit. There we go. Newtons per meter squared. Okay, so put it down there on the bottom. That's all right. So that's our stress problem. Hopefully that was a little bit helpful there for you guys. All right. Now let's talk about strain. Strain is the change in length, or delta L, over the original length, L naught. The way we find delta L is we take the new length and subtract from it the original length. And you could call this L subscript n if you wanted to for new length, and then old length, but L naught means the original, and then they just use L for the new one. So our elastic modulus, the strain is the change in length over the original length. We're going to talk about this elastic modulus here in a little bit. Let's go to a practice problem here. All right, so our strain problem here. A copper wire has an original length, or L naught, of 1.5 meters. It is stretched to a length of 1.52 meters, so that's going to be L. What is the strain on the copper wire? All right, so what I've done here is I've went ahead and put the equation here. L, the new length, is 1.52. It hopes it, there we go, 1.52 minus 1.5 divided by the original length of 1.5. Well, that gives us then, I'm just going to put S here for strain, of 0.02 divided by 1.5. Well, that's going to give us an answer of 0.013. Some of you might be asking, well, what's our units here? Well, length is meters divided by meters, because we have meters on top. Meters minus meters is still meters, divided by meters. Well, what do meters and meters do to each other? They're going to cancel out. So what I want you guys to understand here is that strain is unitless. All right, strain is unitless. There we go. All right, changes in length, shape, and volume are described by Young's modulus, the shear modulus, and the bulk modulus, respectively. Though, right now we're going to talk about Young's modulus. Young's modulus, today I've used this y up here, this Greek-looking y, equals force over area. Well, what have we learned that to be? Force divided by area is stress. The change in length over L naught, or that's L minus L naught over L naught, is the strain. So Young's modulus is also stress over strain. Here's a chart. You're going to want to use this. I don't know if you want to take a snippet of it or take a picture of this. Somehow get this, because you're going to need this today with your homework. But what this is this gives us Young's modulus, Shear's modulus, and Bulk's modulus, the bulk modulus, for different types of materials. So let's look at our problem here over Young's modulus. A 5 kilogram object is supported by a nylon wire of length 1 meter and diameter of 1 millimeter. How much will the wire stretch? Okay, so what I've went ahead here and did here is I've put in a lot of information to start off with. Remember, Young's modulus is stress over strain, and what I did is I looked up Young's modulus for nylon already. Right here, nylon, 5 times 10 to the 8th. So I've plugged that in, and then stress is the force over the area. So the force here is going to be the weight of the object in the area over the strain. So what I'm going to do here is I'm going to solve for the strain. All right, and follow me with this. The weight turns out to be 49. That's 5 times 9.8, and then the area, if you take the 1 millimeter, change it to 0.001 millimeters, but that we don't want the diameter. We got to use the radius and take that times, square it, take it times pi. We get 7.85 times 10 to the negative 7th, divided by strain is equal to 5 times 10 to the 8th. So what that gives us then, so what I've done here is they've told us that the Young's modulus, all right, is 5 times 10 to the 8th is equal to 49 divided by 7.85 times 10 to the negative 7th, which I changed this 49 times 7.85 times 10 to the negative 7th to 62,420,382. Then using some simple math, you can take what the answer is equal to and exchange it with the denominator. So the strain comes out front and the answer goes underneath it. So I now have that the strain is equal to the 62 million divided by 5 times 10 to the 8th equals 0.12. Okay, so I didn't like how that was working out for you, so I tried to make it a little bit more easier for you to see. So what we've learned is this turns into this up top, and what we've learned in algebra is that you can exchange your answer with the denominator. So what we did here is I put the answer in the denominator and took the variable that we were trying to solve for, strain, and made it our answer. So what that gives us now is the strain is equal to 62,420,382 divided by 5 times 10 to the 8th, which gives us 0.12. Well, how does that help us then? So what that tells us then is that the strain is 0.12. So I've given us our strain equation. Again, here strain equals L minus L naught divided by L naught. If you put 0.12 in for the strain, that gives us L minus, well, the original length here is 1 meter. So that's 1 divided by 1. Well, what that tells us then here is that L has to be equal to 1.12 meters. All right. So how much was it stretched? It turned out to be 0.12 meters. Now that only works out to be exactly the same thing as the strain because we're using ones here. If we used other numbers, the strain wouldn't end up being that exact same number. Um, let's move on. Solids and elastic modulus. So some of you guys have seen this same curve here in POE. Stress is proportional to strain until the strain gets too large. Then a material becomes permanently deformed and finally breaks. So what we see here is as the stress, all right, as the stress is increased, it starts to stretch, all right, and that's why we call this the strain. At some point, the strain starts to really give up and it starts to become weak and it really starts to give way. All right, so it means it's starting to stretch faster and faster, and it doesn't take as much stress to cause that strain. All right, here is its elastic limit, which means that it's no longer going to snap back. It's not going to snap back once we let go of it. All right, it's permanently deformed here now. And once we get to this point, if we keep adding stress, it's going to break. Right? It's no longer going to stay together. It's going to break at this point. All right, shear modulus. Shear modulus. The shear is the force over the area. Well, hopefully you guys are starting to recognize that. The force over area is stress, all right, divided by x. Well, what is x? X is the height of whatever the original object was. Or sorry, x is how far has it been pushed out of position, how far was it pushed, and then h is the height. So my apologies there. X is how far was the force that was applied, how far did it cause it to shear, how far did it cause it to the top part of this to slide over while the bottom did not. So you're changing the form of this. All right, so our shear modulus problem. A 200 Newton force is applied at a 40-degree angle to the surface of the end of a square bar. The surface is 5 centimeters on the side. What is the shear stress on the bar? So I'm going to go back to our picture here. The force here, the force is the 200 newtons. They're telling us here that the height, because it's 5 centimeters on the side, its height is 5 centimeters. We're going to have to solve then for the area because it's a square bar, so that's 5, and then that's 5 in both directions. So that's 25 square centimeters, but we're going to convert it to meters and then get a square area in meters. The only thing we've really got to solve for here is x. All right, we've got to solve for x, and that is our opposite, and they've given us the hypotenuse here of 5. So we're going to use cosine of theta, cosine of 40 equals the opposite over the hypotenuse. So that's how we're going to go about solving this. All right, so what I've gone through here and did is I did a lot of math to try to save us some time here, but I'm going to explain this math. So we have to find the force, the area, the x, and the h. Well, the area is the 5 centimeters, but I got to convert it into meters first. 0.05 times 0.05, which gave me 0.0025 meters squared. The force is easy. That's 200 newtons. That's given to us right there. Then, to find x and h, well, if this is theta, this is the opposite. So that's the cosine. Opposite. Oh, I just did that entirely wrong. Let's go back and make a few changes here. Hold on. So in my haste, it's opposite hypotenuse. Some of you probably realize that that's actually the sine function, and I fixed it as we go back. The h is the cosine because this is the adjacent. So adjacent and hypotenuse. So I went back here to find that x and h, and I fixed it on here now. H is the cosine, 5 cosine of 40, which gives us 3.8 or 0.038 meters. And then the x is 5 sine 40, which gives us 3.2 centimeters or 0.032 meters. So I went ahead and fixed that on there. The force then, to find the shear, all right, what is the shear stress on the bar? Well, that's going to be 200. I haven't did this math yet. Divided by 0.0025. And then that's going to be divided by x over h, which is going to be 0.032 divided by 0.038. It's kind of moving stuff there. So our shear modulus here then is going to be equal to, I don't know what the answer is yet. So our shear modulus here turns out to be 200 divided by 0.0025 is 8,000. 0.032 divided by 0.038 is 0.842. So when I divide them, the shear modulus here turns out to be 9,501 newtons per meter squared. So that's our shear modulus example. Alright, so we've got one last one here to learn about, and that is the bulk modulus. Alright, the bulk modulus simply tells us how much something is, the volume is going to change. So let's assume that we put this in some type of liquid, or somehow we pressurize from all sides, so we get this force pushing on this object. And I'm making hand movements that you can't see right now, I just realized. So we've got these forces from all directions pushing on it, and we're going to shrink this box. Well, that is the bulk modulus. That deals with the bulk modulus. So let's take a look at a bulk modulus problem here. Notice that it's still the stress, but now instead of dividing it by how much it deforms this way in the x and h, we're talking about how much it's deformed by its volume. All right, the change in volume divided by the original volume. So a copper cube is 10 centimeters on each side and is placed in a pressure chamber and subjected to a pressure of 2.5 times 10 to the 8th. Just made it a whole lot smaller on all of its surfaces. By how much will each side be compressed under this pressure? Alright, so our last example here. I went through and found a few things for us here. I know it's been a kind of long video, but we're just about done here. Pressure equals force over area. Well, that means pressure has to be stress, because stress equals force over area. So the stress, or the force over area here, so they're telling us the pressure is 2.5 times 10 to the 8th. So that means that the force over area is 2.5 times 10 to the 8th. So, and then we also know that V naught, they tell us that the copper is 10 centimeters on a side. So I went ahead and changed that to meters, which was 0.01. And if we take 0.01 and cube it, alright, I found a mistake I'd already made there. The V naught turns out to be 0.000001, or 1 times 10 to the negative 6 meters cubed. So let's put some stuff in here. Alright, bulk's modulus is force over area divided by the negative delta V over V naught. And if you change this to a division problem, we get force over area divided by delta V over V naught. Well, how do we do fractions? We change it from a division to a multiplication, and we flip-flop the second fraction here. So V naught turns out to be the 0.00001 over negative delta V. So all I've done here is plugged in the numbers and flip-flop this fraction all at the same time. So if we could take the 1 times the negative delta V, we get just negative delta V on bottom, and then I've pushed these together. Once you multiply those, you get 250. You can then take the delta V, put it for the answer, take the answer, put it back in the denominator, and when you take 250 divided by 12 times 10 to the 10th, you're going to get a negative delta V of 2.08 times 10 to the negative 9th meters cubed is the change in the volume under this type of pressure. Alright, today you guys have a worksheet 9.1. I think it's very similar. I did is I took the book, not sure everybody has the book, and typed it into a worksheet for you. I hope this was beneficial for you guys. I'll catch you on the flip side.